Here's a question. How do you use the model simulation experiment system to test a theory? We'll look at an example. So Newton's theory of gravity is stated as every particle in the universe is attracted to every other particle by a force. And the force is directly proportional to the product of their masses, inversely proportionate to the square of the distance between them. So this is a good theory. This theory has something measurable that we can use to test it, to see if it's correct. How do we go about testing that? How do we use model simulation experiment systems to do it? Well, first you create a model. The model in this case is just an equation that takes the words of Newton's theory, turns them into a model, an equation, a calculation that we can do to calculate force between masses. Of course, the theory doesn't actually tell us what's this constant of proportionality, the gravitational constant G. So that's one of the things that we can use the model simulation experiment system to determine. What is that G? What is that proportionality constant? And that's what we'll do. And often you have to go back and forth between the model and the simulation, a simulation here just being a calculation of the force, and an experiment where you actually measure something and relate it back to your model. So we're going to go through this MSE system and see what we can determine about Newton's theory of gravity. Well, first thing we have to do is design an experiment. We've got the model. Now, what does this tell us? We know force, and we can measure mass. Well, how about if we use one of the masses remain constant, the Earth? So the Earth's mass is constant. You drop something from a tower, the mass of the object is attracted to the mass of the Earth. Pretty simple experiment. You can drop multiple objects in the tower, take the mass of each one, and now we have something measurable. If you know the force between this object and the Earth, then you can calculate the acceleration and the time it takes to fall down. So here's our experiment. We're going to drop some things off a tower, and then we'll carry out the simulation, or really this calculation of how long will it take two different objects to fall, given that you drop them from the same height with no initial velocity, all that stuff. Well, we can do the simulation. We can do the calculation. This is, first semester physics you can use to do this. But you calculate these times using the model then in your simulation or your calculation. You make a prediction about what's going to happen in the experiment. Well, now we go to the experiment. Drop the objects, record the times, or in this case you can say, is there any difference in the time it takes them to fall? Because we know the forces on the objects are different, but according to F equals ma and mass and acceleration, they should still fall at the same speed, hit the ground at the same time. That's what happens in this case. So using those times now, we can refer back to our model and estimate the value of the gravitational constant G. Great. Not only that, we should be able to know from the accuracy of our measurements, we can have some estimate of the accuracy of this gravitational constant G. So the model simulation experiment feeds on itself, informs itself, and improves its own ability to model a physical system. So our model simulation experiment system starts with a hypothesis, and then it uses the models, the simulations, the experiments in a loop to where each model improves each simulation, improves each experiment, and an experiment, the data then feeds back through to improve the model or the simulation. And all these things work together to try to give you a look at what the true system is. In our case, it's some physiological system, maybe cardiac, maybe something else. But ultimately, the practical considerations of the experiment will limit what you can do in your simulations and how you use your model. So you have to be careful about how you design experiments, keeping in mind that what you're really trying to do is validate your models and your simulation and ultimately prove your hypothesis to be true. And all this depends on, in biological systems, with biovariability and your ability to take measurements and the kind of tools and techniques you use to run your simulations experiments. Those are very important to achieve the highest accuracy, and also how you interpret your results. And one thing we're going to do in this class is try to always put some reasonable bounds on how accurate we think the results of our simulations are. Because ultimately, as you know, all models are wrong. It's just a matter of how wrong they are to determine whether we can use them or not.